Welcome to EV Tech Explained. This is the third video in a three-part series looking into Tesla's battery technology. Part 1 examined Tesla's cell choice, and Part 2 examined Tesla's module design. Unlike the cell and module, the battery pack is a smart device which can be actively controlled by the battery management system to maximize performance, to ensure safe operation, and actively adapt its output to prevent excessive, long-term performance capability degradation. Cells are converted to modules through the addition of mechanical frames, bus bars, a cooling interface, and a sensing harness. Each of these elements are further supported to transform modules into a smart and safe battery pack. The mechanical frames of the modules interface with the mechanical structure of the battery pack. The mechanical structure must hold together a battery pack which is greater than 600 kilograms and provide sufficient strength and stiffness for the remainder of the vehicle for both driving dynamics and safety in a crash condition. The modules are connected electrically using high voltage bus bars and are connected thermally with a combination of flexible and stiff tubing. The sensing harness on the module feeds into the battery management system, which acts as a controller for the battery system to maximize performance and safety. Additionally, the battery pack includes fuses to prevent the system outputting excessive current, contactors to engage and disengage the battery pack from the remainder of the vehicle, and input and output connectors to electrically and thermally connect the battery pack to the remainder of the vehicle. The 100 kilowatt-hour battery pack from the Model S and Model X actually possesses an absolute energy capacity of 102.4 kilowatt-hours. The 8,256 18650 cells are arranged into a 96S 86P configuration with a nominal voltage of approximately 350 volts. The weight of the battery pack is just over 640 kilograms, resulting in a gravimetric battery pack energy density of 160 watt-hours per kilogram and 63% of the battery pack being cell mass. Let's take a look at how these values are calculated. The energy capacity is calculated by multiplying the cell capacity by the pack nominal voltage and the number of cells in parallel. The gravimetric energy density of the battery pack is then simply the energy divided by the mass of the battery pack. Given that we know the defined mass of each cell, we can also derive that approximately 404 kilograms of battery pack is cells, and therefore 236 kilograms of the battery pack consists of non-cell components. The maximum power which Tesla can extract from its battery is 567 kilowatts. The power output of our battery pack is primarily impacted by our voltage, which is defined by cell voltage and the number of cells in series, the maximum cell current, which is a property of the cell, and the resistance of the battery pack. The total power output is simply the battery pack voltage multiplied by the battery current. The battery pack voltage when outputting power will be lower than the resting open circuit voltage by an amount we will call V delta. V delta at maximum power is calculated by multiplying the maximum combined cell current by the battery pack resistance. Therefore, to calculate the battery pack maximum power output, we first need to calculate its resistance. Cell resistance is strongly affected by a number of factors, such as state of charge, temperature, and discharge rate. However, for the sake of simplicity, let's work with a value for a 10-second 1C discharge at 25 degrees C of approximately 30 milliohms. The resistance of the wire bond connecting the cells to the bus bars is approximately 1 milliohm per joint, and each bus bar has a resistance of approximately 0.1 milliohms at room temperature. The resistance of a series string, therefore, is the cell resistance plus double the wire bond resistance, as there will be a joint at both the positive and at the negative terminals, all of which shall be divided by the number of parallel cells. This yields a resistance of 0.372 milliohms. The module resistance is therefore the series string resistance plus half of the busbar resistance, which is then multiplied by the number of series cells within the module. This yields a module resistance of 2.53 milliohms. In addition to our module resistances, we have the resistance of our high voltage bus bars connecting the modules, which is approximately 0.02 milliohms. The resistance of our high voltage contactor is approximately 0.2 milliohms. Our main fuse resistance is 0.23 milliohms. The resistance of the shunt resistor, which enables the battery management system to measure the pack current, is 0.05 milliohms, and the high voltage connector resistance is 0.2 milliohms. The pack resistance is then calculated as the module resistance multiplied by the number of series modules plus the resistance of the module-to-module bus bars, plus the resistance of the contactors, fuse, shunt resistor, and high voltage connectors. This yields a total pack resistance of 41.8 milliohms. The cell resistance accounts for approximately 80% of the total pack resistance. With this information, we can derive that at a maximum power output of 567 kilowatts, our pack current will be 1800 to 2000 amps, depending upon state of charge and cell temperature. This results in a cell current of 21 to 23 amps, which is equivalent to 6.2 to 6.7 C per cell as a short duration peak power. The mechanical structure of the pack holds together the over 600 kilograms of battery pack and is the foundation for the support of the remainder of the vehicle. It is designed to provide sufficient stiffness and rigidity to enable the vehicle to possess good driving dynamics and to pass challenging crash tests. Thick, longitudinal members add resistance to side impact and longitudinal bending, whilst thick cross members also support side impact resistance and provide additional torsional stiffness. Further internal sectioning is put into place to physically separate each module, which is helpful in suppressing or preventing fire propagation were such an event to occur within one module. Results published by AVL show what happens to a cell when it undergoes nail penetration, a test which is mandatory for Chinese safety testing, and when it is held at very high temperatures in an oven for prolonged periods of time, as per SAE requirements in the US. Under each of these abuse tests, fire is possible, therefore it is important to have a fire suppression strategy in place for the battery pack. So let's take a look at that fire suppression strategy. Beginning with the modules themselves, mica sheets are used around the module and provide electrical isolation between modules, but are also very stable at temperatures up to 900 degrees Celsius, and therefore, in the event of a cell failure, will not immediately break down, thus maintaining appropriate module-to-module electrical isolation. Each module is also separated from other modules with metallic plates. Both above and below the modules, metallic sheets enclose the battery pack, and a 9.3mm thick layer of insulation prevents the direct passing of heat in the event of a failure into the passenger compartment of the vehicle. In the event of cell failure, significant gas pressure will be generated, therefore it is important to have a venting strategy at the pack level. As each module is physically separated, each of these physically separated modules must have its own venting port, with the exception of the two modules at the front of the pack, which are stacked one on top of another, which share a venting port. The fluorosilicon plugs used in the venting ports provide a good seal to the battery and do not degrade significantly with age. When in the presence of hot gases, they break down rapidly, allowing the hot gases to pass through the vent hole. The high voltage bus bars connect the 16 modules in series, with the red side of the bus bars depicting the positive terminal connection and the black side depicting the negative terminal connection. The bus bars themselves are copper-plated tin and have a cross-sectional area of 75 square millimeters. Longer module-to-module bus bars are used to connect to the front two stacked modules via the main fuse. Publicly available results of the tests conducted by AVL on the 100 kWh battery pack provide good information about the cooling system. The test in question here is repeated 250 amp charge and discharge cycles until a steady temperature is reached. 250 amps is roughly equivalent to 90 kilowatts. The test began at 20 degrees C and was run with a coolant flow of 5 litres per minute. In this diagram, the cold side of the coolant is shown in blue, whilst the hot side is shown in red. The coolant is split from the inlet to service each of the 16 modules in parallel. The hot side, which outputs from each module, also connects in parallel to the hot outlet of the battery pack. Each module contains 2 temperature sensors, which enable measurement of a cell temperature near the module cooling inlet and a measurement of the cell temperature near the module cooling outlet. It is desirable to minimize cell-to-cell temperature variation, as hotter cells will be worked harder and degrade faster. It is seen that under these test conditions, pretty significant temperature differences arise, with almost a 10-degree temperature difference across the pack and an almost 8-degree temperature difference over some modules. The large temperature differences between the cells near the inlet and the outlet of the module arise as the coolant runs through the module in a series fashion. Hence, is hotter towards the outlet than towards the inlet. The cooling system does, however, seem to do a good job at preventing cell temperatures from becoming excessively high. Tesla's battery technology will go down in history as a key technological advancement which has disrupted the automotive industry. A little over 5 years since the launch of the original Model S, studies show that the real-world battery lifetime and performance continue to surpass expectations. Can Tesla maintain its lead in battery technology, or will it be surpassed by the larger traditional car makers? What are your thoughts? Let me know in the comments below. If you enjoyed this video, please press the like button and subscribe to this channel. If you have any ideas for topics for future videos, please leave them in the comments below. And if you haven't already, please check out parts 1 and 2 of this 3-part series.